Hello friends, welcome once again. In this session we are going to discuss major problems encountered in FM receiver. There are mainly two problems in FM receiver. First is capture effect and second is threshold effect. During transmission of FM wave via channel, there may be possibility of interference by some other FM wave whose frequency is very close to the main FM signal. When this interference signal is weak, then the received signal is called desired FM wave. Also, when interference is very strong, then the received signal becomes undesired FM wave. But the main problem arises when strength of both desired as well as undesired FM are nearly equal. And due to this, fluctuation occur back and forth between desired and undesired FM wave, and this phenomena of fluctuations is called as capture effect. Next, to understand threshold effect in FM, we consider output signal to noise ratio or post detection SNR, which is equals to 3 AC square KF square P upon 2 N naught W cube. And this is valid after consider carrier much larger than noise, which means carrier to noise ratio at the discriminator input is large compared to unity. But because of some undesirable circumstances in transmission, if input noise power increases, this will decrease carrier to noise ratio, which damages the FM receiver. Initially, individual click sounds are heard at FM receiver output. If further carrier to noise ratio decreases, more clicks found and get merged rapidly and convert into crackling or sputtering sound. So we can say output's SNR become large as compared to actual value. So there is a requirement to maintain carrier to noise ratio minimum, called as threshold effect. This minimum carrier to noise ratio improves the noise performance in FM and minimizes the deterioration from the actual value of output SNR. So friends, our main motive is to overcome these major problems at the FM receiver. For this, pre-emphasis is introduced at the FM transmitter and de-emphasis at FM receiver. As we know, in FM receiver, transmission bandwidth allow to improve noise performance, and according to figure of merit, noise spectrum is accordance with the square law. While transmitting at a very high frequency, the effect of noise is very severe, which introduce interference in FM wave. And to understand this, we consider power spectral density of noise at FM receiver output as shown in figure A and given by S and not function F. Also, power spectral density of message signal such as audio and video is shown in figure B and denoted by S suffix M function F. And both power spectral density are band limited to plus minus W. In power spectral density of noise, we see zero value at F equals to 0 and increases up to plus minus W. But in power spectral density of message signal such as audio and video signal, there is a maximum value at F equals to 0 and decreases accordingly and becomes 0 at plus minus W. Therefore, at high frequency, power spectral density of output noise increases rapidly with respect to frequency, and the power spectral density of message signal falls appreciably. And around the frequency of F plus minus W, message power spectral density become quite low and output noise power spectral density become quite high. And because of this effect, message signal, especially music signal, is not able to utilize its own allotted bandwidth very effectively. So there is a requirement of any other efficient way to utilize this allowable frequency bandwidth. And this method is based on modification in FM communication system. At the transmitter, we have to do pre-emphasis process, and at the receiver, de-emphasis is performed. That is shown in figure. First, at the transmitter side, weaker high frequency component of audio signal are boosted up before modulation using pre-emphasis filter denoted by capital H pre-function F. Similarly, at the receiver, demodulator output is passed through de-emphasis filter denoted by capital H de function F. The performance of the de-emphasis filter is just inverse of pre-emphasis filter. This de-emphasis filter restores the original message signal by altering the high frequency component, and this process of pre-emphasis de-emphasis maintains the desired message signal in its original form but reduces the noise power very effectively. So we can say that at discriminator output, post-detection SNR increase very effectively and hence improve the noise performance in FM receiver. Therefore, we can say for undistorted message signal at the receiver output, the frequency response of de-emphasis filter must be equal and opposite, or simply called inversely proportional to pre-emphasis filter within a bandwidth of plus minus W. Now, as we know that at the discriminator output, derivative noise having power spectral density denoted by capital S and D function F, and it is equals to F square upon AC square into N naught for mod F less than or equals to half of transmission bandwidth and 0 otherwise, and it is also shown in figure. After this, discriminator output is passed through de-emphasis filter, which perform inverse operation to de-emphasize or attenuate high frequency component, and original power spectral density of message signal can be restored. Therefore, output of de-emphasis filter is given by S N naught function F equals to product of power spectral density of derivative noise and square of the mod de-emphasis filter. This S N naught function F is also called as modified power spectral density. And using this output modified power spectral density, we can find average power within bandwidth of plus minus W. So average power of this modified noise is equals to N naught upon AC square integration of F square square of mod de-emphasis filter into DF, taking limit from minus W to plus W. We can also say that ideally, average power of output noise is not affected by pre-emphasis and de-emphasis process in FM system, but the noise performance become better and can be measured by a factor called as improvement factor capital I. And improvement factor capital I is equals to ratio of average output noise power without pre-emphasis and de-emphasis upon average output noise power with pre-emphasis and de-emphasis. So we can say I equals to ratio of 2n naught W cube upon 3 AC square upon n naught upon AC square integration F square square of mod de-emphasis filter into DF. After arrangement, we get improvement factor I equals to 2 W cube upon 3 integration F square square of mod de-emphasis into DF. Here we note a point, improvement factor I is only defined after assuming high carrier to noise ratio at the discriminator input in FM receiver. So higher the value of improvement factor I, better is the noise performance in FM receiver.